Assalamu alaikum and welcome to this video where we will start by discussing about bracketing methods, which will be a continuation of the previous video that has been provided. So let us start with the bracketing methods. First and foremost, as for the bracketing method, we get bisection method, which is also known as binary chopping or half interval method. As we mentioned before, bracketing methods actually require a range, and the value or the root must need to remain in that range, and hence in order for this algorithm to work, it first needs to have two values, which is we will be calling them x1 and x2. And it is essential, the most essential part, that the roots remain between x1 and x2. If there is no root between x1 and x2, this algorithm will not work. Why not? We will explain this. Just stay tuned for a while. After we decide on some initial limits or cases, which are x1 and x2, we have to compute the value of f1 and f2 using f of x1 and f of x2. The question will remain, what is f of x1 and what is f of x2? Well, in the question we will be providing you with the f of x1 or f of x2. We will provide a function actually for which we actually started studying polynomials. If I want to recap a little bit, we will provide a value like x square minus x plus 1, something like this. It will be provided in the question, that probably this part won't be there. X square minus x plus 1 equals to 0. This equation is provided. Find the root of this equation. Based on some initial guess, you have to start working. And now if you are giving some initial guess, for example, if you are given that x1 is initially 1, then you can calculate using this equation. The value will be 1 square minus 1 minus 1, which means we will have minus 1 as the overall value. So we can say that the f of x1 will be minus 1. This is all just a sample, and such you can also calculate the value of f2. Once you got the value of f1 and f2, you first need to see if the multiplication of f1 into f2 is greater than 0 or not. If it is greater than 0, then we say there is no root in x1 and x2 range. Once again, we will explain this in the next slide, but just so you know, the multiplication of f1 and f2, if they result in a value greater than 0, we will say that there is no root in x1 and x2. If that is not the case, then obviously there is a root between x1 and x2, and while we don't find that root, so while true, we using the bisection method, this line is what will change in algorithms as we move on this part. This is called the update rule. X0 over here is the new value of x, which will be calculated using the value of x1 and x2. And once we get the x0, we will get a new f0 as well, and we will say that f of x0. So then once again, if f of 1 into f of 0 is less than 0, then we will update, such as x2 will become x0, and as x2 is taking the value of x0, f2 will be taking the value of f0. Otherwise, if f2 and f0 multiplied to be less than 0, then x1 will be x0 and f1 will be f0. And once the error of x1 x2 is less than the threshold given, ea or er, root will be found and we will break the loop. Now this part over here or this part over here, why are we so much obsessed with the multiplication operation and whether or not they are 0 or not? Okay, so this is actually a very good question or intuition from mathematics that we should understand in order to fully understand why this algorithm or how this algorithm works. So next up is a simulation of bisection method. So let us consider the equation x square minus 4x plus 3. Suppose this is the equation that I need to solve. This equals to 0, and over here we see two red points. Okay, actually I know the answer to this equation. One of the root is 1 and the other root is 3. I know the equation, but the algorithm still does not know. Okay, so these known results, they are pointed out as red, and now I have the equation. So let's say first I'm given the initial guess, which is -3 and -1. So the x1 value is -3 and x2 value is -1 or something like that. If we provide these points in the graph, we can see that when x is -3, the f value over here will be somewhere between 20 to 30, I guess, just between 20 to 25. And for -1, if we look at the graph, we can say the value is very close to 10, somewhere between 7, 8, 9, 10, something like that. So we can easily say if we multiply these two values, the number will be positive number, not a negative number. The answer will be a positive number, because this is also a positive number over here. This is also a positive number, so their multiplication will be a positive number. Just to be sure, let's write this out. I am trying to guess that over here it's 25, suppose, and over here is, let me guess it, 9. Okay, so clearly this is greater than 0. Okay, let's see the next guess. Once again I have guessed 1.5 and 2.75. 1.5 is this point over here, 2.75 is this point over here. Now if you watch very closely, if you zoom in, I already shared the PDF file in the classroom. If you look very closely over here, the value is in the negative side of the x-axis. Over here is the x-axis, so in the negative side, so we can say that the value of y over here is negative. Suppose that for this point, this negative value, I don't know, maybe 0.2, minus 0.2, and over here is another, suppose, I don't know, maybe minus 0.23. Let's just guess the value, something like this. What will happen if we multiply these values? It will again be a number which is positive, that is greater than 0. And look carefully, there is actually no root between these two numbers, so this also satisfies what we know as the fact that there is no root between these two places. Hence, this is why we first checked. Okay, before that, let's go to the final example. -1 and 2 is now our guess. Now if we look at this point, we can say that it's somewhere around over here. So let's say he is 8 and this part is in the negative range, so we say that this is something like -0.1. The result over here will obviously be a number which is less than 0, and thus this is why we did that checking, that is the number, the multiplication of the f of x values are less than 0 or not. If they are less than 0, we claim that there was a root in between, and that is all the reason we did that checking, and we kept on checking whether or not the value remained between these two ranges. And thus now we have those guesses, which is -1 and 2. So now we know that, yeah, we just got the right guesses on. Now we need to get the answer. So now, using the equation of bisection method, which was, if we can rewind or we can pause and go to that slide, we add these two numbers and divide them by 2, we get the new value of 0.5, and it is shown over here in the green point. Now if you look very closely, suppose this is x2 and this is x1 and this is our new x0. Okay, let's just write it out. I'm claiming this point to be x2, I'm claiming this point to be x1, and I'm claiming this point to be x0. Now if we calculate the f of x0, f of x2 and f of x1, we will be able to see that the answer lies between f of x1 into f of x0 will be less than 0, and actually we don't need the x2 value anymore. In fact, if we update the x2 to be this point later on, we are actually closing in on the answer. Okay, if we can delete this point and make this another guess, then we will be searching between these two ranges, so it will be a much better initial guess, if I am to say so. And that is exactly what we will do. We will keep 2 unchanged and change -1 to 0.5, and then we will run bisection method again, and now we got another guess which is 1.25. Look very carefully. Once again the gap is closing in, and now this new root is actually better than the one we saw before. So now we update it again, and now we are again closing in, and as you can see, after each iteration the gap between the two guesses are actually decreasing. And that is why while checking the while the algorithm was running, if you remember carefully, I would like to go back to the slide over here, we were checking the difference between the two guesses. Okay, this is why we were checking the difference between two guesses. If the difference between the two guesses are very small, we can say that okay, we have closed in on the answer, we got the answer, so we do not need to waste our time anymore. Hence that's why our error checking was done over such a small part. Okay, then let's move on. We have next false position method. It does exactly, it's completely same as the previous method, only one thing changed is the update rule over here, and nothing more or nothing less than that. This is the only change from bisection method in false position method. So other than that, there's nothing. We in this course we do not need the derivation of this equation. It actually comes very easily using finding equation of lines, but we will not go that much. It's just the update rule that changes. Next up, open-end methods. So we have seen bracketing methods, now we are up with open-end methods. So what are the open-end methods? We have explained before that open-end methods do not have a bracketed zone, rather they have open limits. You can go from any place to any place. So one of those cases, one of those algorithms are the Newton-Raphson method. So we will start up with Newton-Raphson method. In Newton-Raphson method, now we have only one initial guess, which is x1, and we will try to use this guess to find the answer. So what will we do? We will first calculate the value of f of x1. Okay, then we need to find the value, the new guess x1 minus. Okay, now one thing I need to ensure that f of 1, and what is this f prime of 1? Well, f prime actually means the first order derivative. If a function is given something like this, it means the first order derivative. If something is given something like this, is the second order derivative. In other words, I need to calculate d dx of f, and that will be the f prime of my equation. In order for Newton-Raphson method to work, hence we need the differentiation, and once we get the new value x0, we will calculate the difference between the previous guess and the current guess, and if it is less than the result, same system that we have closed in on our target, and hence we will break, and if that is not the case, then we will continue on the break. Okay, so how does the Newton-Raphson method actually close in on, or how we, in previous case we have seen that we need two places to actually block the answer from getting away. So how does the Newton-Raphson close in? So let's see another simulation over here. So we get the equation x square minus 4x plus t, and its first order derivative is twice x minus 4. So let's see in the same equation how does it work. We provide an initial guess of -2. Okay, now we do not need to have a checking whether this guess is correct or not. We just give this number, and if we use the values and put them on, we get the new guess is -0.125 over here shown. This is the guess, and this is the value we have found. Okay, -0.14. Look at that. Over here was the guess, and already it's closing in one of the roots. Okay, next up. So when we take this one, it again closes it even more to the root, and in the next step you can see it's almost aligned. Now if you look very carefully, we have already got 0.9658. okay, so in my guess this root is 1, so we have really closed in, and this is how Newton-Raphson method closes in on its target. This is how Newton-Raphson gets the answer it wants. In second method, though we need two initial guesses, this actually still is an open-end method. That is, the root need not to be within these two given points, and it can be outside. Just for the equation to work, we are going to need two initial guesses, and here they're given. And after that, we calculate the values and make this update. It works same as the previous method, no changes made. For practice, we will try doing that when we get the time, but the process is actually exactly same as before. Okay, fixed point iteration is also same, but there are some special cases for this. For example, you have been given x square minus x minus 1 equals to 0, an equation like this. Okay, you can rewrite this equation. In actual fact, you can write it like x equals to x square minus 1, right? Or you can also write it like something like this, x plus 1 by x. So functions like this, they will be given the name g of x. Okay, we will call them g of x for fixed point iteration. Okay, so fixed point iteration needs you to provide a function at first, and needs you to provide what is the g of x of that function. So it is not, unlike the other methods, it's not so very universal for you to work with. But fixed point iteration is very straightforward. You just need to use the g of x and take the previous value and update it and do this. It's very straightforward. The calculation mechanism is very easy, but these parts you have to do it manually. And there is another constraint: for fixed point iteration to work, g of x must follow this rule. Once again, you see the prime, which means the first order derivative. So the first order derivative of x must always be absolute, value must always be less than 1. If not, fixed point iteration will not work. This is a limitation of fixed point iteration, so we will not do much of this task in the exam as well, but this is an algorithm which is valid. So that is it for this video. We will discuss the last topic of the slide, which is finding all roots, once in the next video, inshallah. So thank you very much everyone. Assalamu alaikum.